Hey guys, I'm back on the channel with a crazy question. So the question that you see on the screen is taken from the question papers of one of the coaching institutes. I was casually solving the question paper and then I encountered this monster. So you see two expressions here, P and Q. Absolutely huge. Each one of them is absolutely huge. Looks, you know, very scary. And P upon Q is given to you. Let's look into the expressions. Trust me, by the end of this video, you're going to learn a lot. This video is going to be a banger video. So make sure you stay tuned till the end of it. So let's look at the expressions. So you have P. First thing, you have 1 by 2, 1 upon 4, and then 1 upon 8, 1 upon 16, 1 upon 32, 1 upon 64, and all of those terms which are there in geometric progression. Next, cos, sine, cos, sine, cos, sine, cos. So the angle varies from theta, 2 theta, 3 theta, 4 theta, 5 theta, and so on that way. But again, one of the weird things is the sign. So first term is positive and after that it strictly follows a pattern. Twice you're getting a minus and twice you're getting a plus. Again twice minus and then twice plus. And the series continues and it is an infinite series. And that is your P. Now you have another scary and huge expression for Q. Similar fashion, first term is positive and then there are two negative signs, two positive signs, two negative signs, and then two positive signs, and it goes on. And it starts with 1 half, 1 upon 4, 1 upon 8, 16, 1 upon 32, 64, 128, and so on. Geometric progression again. And then here sine theta, cos 2 theta, sine 3 theta, cos 4 theta. So if the angle varies like this, what do you do? And the question is so beautiful that they gave you the ratio of P upon Q. How on earth are you going to find out this particular ratio? Initially, I was clueless and it took a hell lot of time for me to solve this particular problem. So you have this ratio and then you have to tell the number of values of theta which satisfies this particular ratio and which exists in the interval minus 3 pi to 3 pi. It took a hell lot of time, trust me. And after a lot of struggle, I managed to solve it. And I'm going to present the solution today. So, okay. So now, at the first glance, you must be thinking that it is a trigonometry question, but it's not. The question is from complex numbers. So let's see what we can do. So you have cos theta here and then sine theta here. All right. So let us forget about this ratio and what is asked in the question, all of that. Let us try to, do something. So you can just follow me. So this is a cos theta term, sine theta term. Again cos theta, sine theta. So it makes sense to add these two series. So that you can put all the theta terms at one place, 2 theta terms at one place, 3 theta terms at one place. We also know the Euler's formula. It is cos theta plus I sine theta. So instead of simply just adding these two terms, I'm going to do Q plus I times of P. Okay, Q plus I times of P. All right, that's what I'm going to do. I can also do P plus, all right, P plus I times of Q. You can ask me why I am not doing this. I am not doing this because when I multiply this Q with I, so this 1 which is a constant term, it gets multiplied by I and then that generates an imaginary term, and I don't want that. I want imaginary terms, I mean the I terms, to be there with only cos thetas and sin thetas. You can do this and check what happens. Okay, so I just want to retain this 1. That is the reason why I'm doing Q plus P. So let's see what we are going to do, what we are going to get when we do Q plus P. So the first term will be 1 and then second term is negative sine theta plus I times positive cos theta. So minus I sine 2 theta plus I times half of cos theta. Next comes 1 by 4 and then so negative cos 2 theta, negative sine 2 theta. All right. So minus cos 2 theta minus I sin 2 theta plus 1 upon 8, and with 8 you will get sin 3 theta minus I cos 3 theta, sin 3 theta minus I cos 3 theta plus 1 upon 16. With 16 you will get cos 4 theta plus sin 4 theta, I sin 4 theta, cos 4 theta plus I sin 4 theta. So let us write one more term, plus 1 upon 32, and then here you will get minus sin 5 theta, minus sin 5 theta, and then plus I cos 5 theta, plus I cos 5 theta, plus and so on. So this is what you are getting. All right. So now this is simply 1 plus half into, okay, let's do one thing. So this is simply 1 plus half, and let us take I common. Then you will get cos theta minus I sin theta. So if you observe, this will give you I cos theta term, this term, and then I into I is your minus I square, which is plus. So I into I will give you I square, which is minus 1, and that will give you this term. All right. Plus similarly, here you can do minus 1 upon 4 is common, and this is simply cos 2 theta plus I sin 2 theta. All right. Plus, so now I'll take minus 8, 1 upon 8I common. Then you'll get cos 3 theta, cos 3 theta plus I sin 3 theta. All right. This is what you're going to get. Now here 1 by 16 is common. This is simply cos 4 theta plus I sin 4 theta. Next I'll take plus 1 upon 32 I common, and then cos 5 theta, all right, plus I sin 5 theta. This is what you'll get. See how beautiful this is. So now this equation becomes q plus ip, q plus ip is equals to 1 plus I upon 2 e to the power I theta minus 1 upon 4 e to the power 2I theta minus I upon 8 e to the power 3I theta plus 1 upon 16 e to the power I 4 theta plus I upon 32 e to the power 5I theta plus and so on. So this is what you have. Now, even now we have something to manipulate here. All right. So let's do some manipulations. 1 plus I into e to the power I theta divided by 2. Now this minus 1, I'll write it as I square. I square e to the power 2I theta divided by 4. And this minus sign, I'll write it as I square. So that will become I cube e to the power 3I theta upon 8. Plus this 1 can be written as I to the power 4 e to the power I 4 theta upon 16. This I can be written as I to the power 5 upon 32 e to the power 5 I theta. See how beautiful it is. So if you consider I times e to the power I theta is equal to some t, let's say, then this will become 1 plus t upon 2 plus t square upon 4 plus t cube upon 8 plus t power 4 upon 16 plus and so on. Now it is an infinite GP with common difference t upon 2. The formula will be a upon 1 minus t by 2. So this is your q plus ip. So 1 upon 1 minus half, your t is I times e to the power I theta, that is simply cos theta plus I sin theta. Alright, now let us simplify this. See how beautiful it is. So the most clumsy and crazy terms, there were the sequences itself were crazy, huge. All these got converted into a beautiful infinite geometric progression. So this is the beauty of mathematics, and this is the reason why you should pursue mathematics. This is one of the reasons why I love mathematics personally. So let's go ahead. So 1 upon 1 minus I cos theta upon 2 plus sin theta upon 2. This is what you get. Now just rationalize 1 plus sin theta upon 2 plus I cos theta upon 2 in the numerator, and the denominator also same thing. 1 plus sin theta by 2 minus I cos theta by 2 is already there. You are going to multiply this with 1 plus sin theta upon 2 plus I cos theta upon 2. Alright, let us simplify the denominator first. So a minus b into a plus b, that is simply a square plus b square cos theta by 2 whole square. Alright, in the numerator you will have 1 plus sin theta by 2 plus I cos theta by 2. Now in the denominator let us simplify. So 1 square is 1 plus you have sin square theta upon 4 plus sin theta plus cos square theta upon 4, and in the numerator you have 1 plus sin theta by 2 plus I cos theta upon 2. So in the denominator, if you check, this term will give you, these two terms will give you 1 upon 4. So 1 plus 1 upon 4 is simply 5 upon 4 plus sin theta, and in the numerator you have 1 plus sin theta by 2 plus I cos theta by 2. So this is q plus ip. Compare real terms and imaginary terms and you'll get q is equals to 1 plus sin theta by 2 upon 5 by 4 plus sin theta, and p is equals to cos theta by 2 upon 5 by 4 plus sin theta. Alright, let us simplify these. So 2 plus sin theta by 2 by 5 plus 4 sin theta upon 4. So that will give you 2 times of 2 plus sin theta upon 5 plus 4 sin theta. Alright, and here you'll get p is equals to cos theta by 2 by 5 plus 4 sin theta by 4, and that will give you 2 cos theta upon 5 plus 4 sin theta. Alright, so finally we are able to find out the values of p and q. Alright, now the next thing to do is to consider this. P upon q is equals to 2 root 2 upon 7. So p upon q is equals to 2 root 2 upon 7. So what is p? This is p, 2 cos theta by 5 plus 4 sin theta. 2 cos theta upon 5 plus 4 sin theta divided by q. Q is 2 times 2 plus sin theta upon 5 plus 4 sin theta. This is simply 2 root 2 upon 7. So this and this gets cancelled, and you'll be left with 2 cos theta upon 4 plus 2 sin theta is equals to 2 root 2 upon 7. This is what you have. This 2 and this 2 will get cancelled. Now cross multiply. 7 cos theta is equals to 4 root 2 plus 2 root 2 sin theta. This is what you have. Now 2 root 2 sin theta minus 7 cos theta plus 4 root 2 is equals to 0. And that's what you have. Now what do you have to do? You can do one thing. So you can write it as 7 cos theta minus 2 root 2 sine theta is equals to 4 root 2. This looks like, okay, we have to find the general solution of this equation. Number of values of theta that satisfy in minus 3 pi comma 3 pi. So this is what we have to find out. All right, so that's what we have to do. So let's do that. So let's divide this equation on both sides by square root of 7 square plus 2 root 2 whole square. Root of 7 square plus 2 root 2 whole square. So why 7 and 2 root 2? Because we have these coefficients here. This is a very pretty standard technique. 7 cos theta minus 2 root 2 sine theta upon 7 square is 49. 2 root 2 whole square is 8. So that will give you 57. Alright. So root 57 is equals to 4 root 2 upon root 57. So now this looks something like sine theta, sine alpha cos theta minus cos alpha sine theta is equals to 4 root 2 upon root 57. So this is simply sine alpha minus theta is equals to 4 root 2 upon root 57. So alpha minus theta is equals to sine inverse of 4 root 2 upon root 57. So theta is equals to alpha minus sine inverse of 4 root 2 minus root 57. Alright, but we have to find out what alpha is. So we know sine alpha from here as 7 upon root 57. So alpha is equals to sine inverse of 7 upon root 57. So theta is equal to sine inverse 7 upon root 57 minus sine inverse 32 root 32 upon root 57. This is what we have. So this is an angle theta. So here you can apply sine inverse x minus sine inverse y formula. Sine inverse x minus sine inverse y. So that will be simply sine inverse of x root 1 minus y square minus y root 1 minus x square. So this is what you get. So that will be sine inverse x is 7 upon root 57 square root of 1 minus y square. So that will be 1 minus 32 upon 57. So that will be 25 upon 57 minus y root 32 upon root 57 square root of 1 minus x square. That will be simply 50 upon 57. This is what you have. So sine inverse. So in the denominator you will have 57 here. Even here you will have 57. So numerator this is simply 5. So that will be 35. And here this is 4 root 2 and that is 5 root 2. Alright. So this is 4 5 is 20, 22 is 40. So sine inverse 35 by 57 minus 40 by 57. So sine inverse negative 5 upon 57. So this is what you have. Alright. So you have kind of sine theta. So this is theta. So you have kind of sine theta is equal to minus 5 upon 57. You know how to find out the roots. So this is the sine function. Alright. Minus 5 upon 57 will be somewhere here. Okay. So you will have a total of 1, 2, 3, 4, 5, 6. 6 solutions. And that is the answer to this question. So your key takeaway should be that when you see all these kind of, scary and insanely difficult looking questions, so you should not be scared and you should put some time to analyze those questions. And whenever you see lot of theta 2 theta 3 theta 4 theta 5 theta and all this kind of stuff, you should not think about like you should I don't say you should not think about trigonometry, but you should also think about complex numbers. All right. So initially there was no pattern found. So there was a cos, sine, all of this, change of trigonometric ratios, and then there is a geometric progression 1 upon 2, 1 upon 4, all of that. And then there are, two negative signs, two positive signs. The pattern was not at all visible. So in such cases, just go and blindly try to, make use of complex numbers and somehow generate a good looking complex number, you know just to exploit the Euler's formula. All right, and that's how we arrived at this crazy and beautiful looking geometric progression, infinite geometric progression. And finally we managed to solve the question. I hope you have liked the video, and if you did, do not forget to give it a thumbs up, share it with your friends, and subscribe the channel for more such content. And if you have any queries, comment section is the way to reach out to me. I'll get back to you with one more crazy question in the next video. Till then, stay tuned, take care.